Section 5.2 The Natural Logarithmic Function Integration. Using the derivative for the natural logarithmic function to obtain an antiderivative. Example number 1, we want to find the antiderivative of the function capital F of x equals ln of absolute value of x. So we will begin with the definition. Ln of absolute value of x equals integral from 0 to absolute value of x 1 over t dt. When x is bigger than 0, the absolute value of x is the same as x. So we will get integral from 0 to x 1 over t dt. And if we need to take the derivative for this expression, according to the second fundamental theorem of calculus, we get 1 over x. On the other hand, when x is less than 0, ln of absolute value of x is the same as ln of negative x. So we get, by definition, ln of negative x is integral from 0 to negative x 1 over t dt. Now remember, when we take the derivative of an integral, that is ln composed with negative of x, we have to use the second fundamental theorem and the chain rule. So we get the integrand evaluated at negative x times the derivative of negative x, which is negative 1. So the derivative is still 1 over x. So either way, we note that ln of x has the same derivatives as capital F of x, which equals ln of absolute value of x. Therefore, we call capital F of x as an antiderivative of little f of x equals 1 over x. And we have this integration formula. Integral of 1 over x dx equals ln of absolute value of x plus c. Now we will apply this integration formula to solve some definite integral and indefinite integral. So let's take a look at the integral in example number 2. It might not be obvious that you will see we will need to use the integral of 1 over u. But if you observe the function x squared and x cubed, x squared is 1 degree less than x cubed. So we suspect we might need to use the u substitution that we learned in chapter 4. So as usual, we will set our u to be a function inside a parenthesis under the square root or in the denominator. In this case, we have x cubed plus 4. Then our du will be 3 times x squared dx. So we can rewrite the original integral as x squared dx will become 1/3 du, and the denominator will become u. And this is a simple integral. Applying the formula that we just learned, we get 1/3 ln of absolute value of u plus c. Now it's important that you write down the absolute value of u, because when sometimes the expression could be negative, we still will be able to evaluate the integral. So it's important that we take the absolute value, because the domain of the Ln function is positive real numbers. So for the last step of u sub, we have to substitute the expression of u back. We get x cubed plus 4. So the antiderivative of x squared over x cubed plus 4 is 1/3 ln of absolute value of x cubed plus 4 plus c. Example number 3 is a definite integral, and it's a very simple one. So when we evaluate, we want to take out the constant. We don't need to use u sub because it's a very simple integral, 1 over x dx. According to the integration rule, antiderivative of 1 over x is ln of absolute value of x evaluated from 2 to 5. So we have 1/3 ln of absolute value of 5 is just 5. Subtract ln of absolute value of 2 is just 2. And we want to combine this expression, we get 1/3 ln of 5 over 2. You can actually evaluate this using your calculator. Now, if you take a look at example number 4, you will notice u sub doesn't work because the derivative of the denominator does not give you the numerator. So we will have to apply the long division technique that we learned from pre-calculus. So we will break down the integral, or break down the fraction into 3 fractions, because the numerator have a higher degree. So we have x to the 7th divided by x to the 5th minus x over x to the 5th plus 3x 4th divided by x to the 5th dx. Now we simplify, use and rewrite everything in power form. x7 divided by x to the 5th, we get x squared minus x divided by x to the 5th, we get x to the -4th power plus 3 times 1 over x. And we want to keep it as 1 over x because the antiderivative doesn't follow the power rule. So according to the power rule, the antiderivative will be x cubed over 3 minus x to the -3rd power divided by -3. So we change that to a plus sign. Plus 3 times ln of absolute value of x plus c. And we are done. Example number 5. Then we notice the derivative of the numerator or the derivative of the denominator does not give each other. So we will not be able to use u sub, and instead we will have to do long division or separate the fraction. So we combine x squared plus 1 plus x. And the reason we group x squared plus 1 together is because it looks exactly like the denominator. And we break this fraction into 2 fractions. So for the first fraction, we simply get 1. And for the second fraction, we can actually use u sub. So let me rewrite it. I'll break the fractions. Okay, so for the first integral, we should get x back. But for the second integral, we have to use u sub, so we set u equals x squared plus 1. And our du will equals 2x times dx. So x dx is just 1/2 du. So we have to add 1/2 du over u. And according to the formula of the antiderivative of 1 over u, we get ln of absolute value of u plus c. And the last step is just to replace the u expression by the expression involving the original variable. Next, we're going to study more integrals of the trigonometric functions. So first, let's take a look at how to derive the antiderivative of tangent of x. We rewrite tangent of x as sine of x over cosine of x. And we will apply the technique that we are very used to, which is the u sub. And the location for u are usually inside the parenthesis, under the square root, or in the denominator. So in this case, our u is cosine of x. Our du will equal cosine of x negative sine of x dx. So we can rewrite the original integral as integral sine of x dx will become negative du. Cosine of x is u. So the antiderivative is negative ln of absolute value of u plus c. And now we have the antiderivative of the tangent of x equals negative ln of absolute value of cosine of x plus c. You may suspect that we can use the same idea to calculate the antiderivative of secant of x. So if we rewrite secant as 1 over cosine of x, if you want to set cosine of x equals u, you might realize the problem is we don't have any sine of x. And in fact, if we want to derive the antiderivative using the definition, we will have to require a new technique that we're going to study in chapter 8, an integration technique called partial fraction. So we cannot go this route, so at this point, and we have to employ a slick way. So we pull our function or an expression out of the hat. We say, okay, we want to multiply secant of x by 1. And we want to write 1 in the form of secant of x plus tangent of x. And you might wonder, how do we get this expression? Well, if you do know the partial fraction technique, you can derive the antiderivative using just a definition of secant of x, and you will realize the answer involves secant of x plus tangent of x. So that's how we get this expression. So now if we rewrite this expression, we get secant square of x plus secant of x times tangent of x divided by secant of x plus tangent of x dx. And if we set the denominator as our u as usual, the numerator times dx will be our du. So we get du over u. And in this case, the antiderivative is ln of absolute value of u, which is secant of x plus tangent of x plus c.